So if you've taken algebra in high school, you probably might be panicking a little bit with the name of this section, logarithms. They are notorious mathematical things that a lot of people struggle with. And I don't want to kind of belittle that struggle, and I definitely don't want to say this section is easy because it's not easy, but it's also not as terrible as a lot of people make it out to be. And in fact, what I've kind of been mentioning and building up to is that if you are good with exponentials, you'll probably be pretty good with logarithms. It's just a lot of people miss that key connection that one is the inverse of the other. And that is also to be said if you don't know basics like what's 2 to the third or what's 3 squared or even what's 3 to the third, it might be helpful to get like a little small chart online or something like that so that you can kind of see those and maybe even ideally memorize those values so that when we're going through these logarithms you can say, oh, okay, I see where that connection's happening. I see what that exponential value is and that he's talking about, and now I can make the connection to logarithms. Well, I just defined it. A logarithm is the inverse of an exponential. So might not be super comfortable with the term inverse, but one of the most famous inverses, or at least inverse relationships, is addition and subtraction. And that's because when you are solving an addition problem or solving something like x plus 2 is equal to 1, well, you subtract from both sides. Another pretty famous inverse pair is multiplication and division. So that's the entire reason logarithms were quote unquote invented or exist, is that when you have an exponential function and you want to solve it or you want to undo something that has a power, well, you use a logarithm to undo that. So that's the connection. And so we're going to start with a very important part of the process, which is just translations. So in this case, I have b to the y is equal to x. Well, if I wanted to solve for y, if I wanted to get y by itself, I would take the log base b from both sides. And so that would cancel out the b on the left side, and now I'd be left with log base b of x. I say base, that's the thing right next to the log. So anytime you hear me say log base something, that's I'm talking about the tiny letter or number that is to the bottom right of the logarithm. And vice versa. Like if I have a logarithm, y is equal to log base b of x, and I want to solve for x, well, to undo my logarithm, I take an exponential. So I would take b to the log base b of x on the right side. That would cancel my log, and I would be left with b to the y is equal to x on the left side. So to see this in practice, oh, quick note. The domains of logs, the domain of logs is 0 to infinity, and the range of logs is negative infinity to infinity. And if you're really good at kind of putting pieces of the puzzle together, you might notice, okay, well, logs and exponentials are inverses of each other. Well, the domain and the range of a log and an exponential are flipped. So that's kind of where those come from. We'll see that more when we get into graphing, but that's kind of just to hammer home this relationship a little bit more. Now for starters, we're not even going to solve. We just want to be able to translate, because that is the first piece of the puzzle. I said puzzle a lot. That is the first piece of the process when we are solving for logarithms or exponentials or anything like that. So before we get into deep with anything like that, we want to make sure we understand how to get from one to the other. And I will use this term a lot in the next couple of sections. I'll say I'm translating this to that or that to this. This is what I'm talking about. So I have a logarithm. I want to translate it to an exponential. So I have log base b of 3 is equal to b. Well, I look up at my translation on the top of this slide, and to get a logarithm to an exponential, I swing that little number, that tiny number, over to the other side. And so in this case, I would have 3 to the b, and then I'm solving for x. And here I have log base d of 4 is equal to 5. I will move my d to the other side. My right side will become d to the 5th, and I'm left with just a 4 on the other side. We'll see it once more. And in this case, this is actually solving what a log would be like. But again, we're not focusing on that, just the translations. So I have log base 3 of 9 is equal to 2. I'm going to take that tiny 3, I'm going to move it to the other side, so I get 9 is equal to 3 squared. I'm undoing those logarithms. Now to go the other way. I have x is equal to 3 to the b, and just to kind of mention it, I'm sure I've mentioned it before, an exponential, we call that bottom part base as well. So when I say log base b of x, I should also be saying, in this case, the base of 3 to the b. It's just a little bit redundant, it seems kind of clunky, but that is what we call that 3. So in this case, the base of my exponential is 3, so I'm going to move that to the other side, and I'm going to have a log base b, or a log base 3 of x, and now my b is by itself. So I'm kind of isolating b. Here I'm going to isolate my x. Okay, well the base of that exponential is 2, so I'm going to move that to the other side. That's going to become the base of my log. So I will have log base 2 of 8 is equal to x. See it again, I have y to the x is equal to 5, and I kind of put this example out there to emphasize, well, where things are showing up aren't super important as opposed to like the left side of the equal sign or the right side of the equal sign. It's more, what am I translating to? So in this case, I'm going to take an exponential, put it into a logarithm. The base is y, so I'm going to move it to the right side. It'll be log base y of 5, and then I'll have x left. Now I have 10 to the third. Yep, that's certainly 1,000 if I throw it in my calculator. But if I want to translate it to a logarithm, I move the base of 10 over to the other side, and the left side becomes the 3. It becomes that power. So notice how the power in this case is kind of just dropping down on the side, and then the base is moved to the other side with the logarithm. Now, something worth mentioning. There are two very special, important logarithms. The first one is log base 10. We see that a lot when we're talking about scientific notation, for example. You see 10 to the certain power all the time in chemistry and stuff like that. And since we see it so often, we just call it, I believe, the standard log, or we just don't write whatever the base is. So if you have a graphing calculator on you, you might be looking around it to see where the logarithms are. And if it's not a fancy new calculator, there's probably a button that says log, and there's probably a button that says ln. So the log button is taking the log of base 10, so it's that translation. And so if you see just a logarithm when you're working through WebWorks, because they definitely like to do this a lot, or I'm talking about it on the lecture, and you don't see a base, assume that base is 10. Now, the second log that is super important revolves around that concept that we brought up last lecture, is this e guy. So e seems like it's a variable because it's a letter, but it's actually a very, very important number, and we use him so often that instead of writing him out, we just call him e. I think it's 2.71312, I want to say. And so, again, not really super important to this application. Really, we want to try and translate this question. So I have e to the x is equal to 7. To translate it, my x drops down. My e becomes the base of my log on my right side, and it will be log base e of 7. Now I mentioned in part D, oh, these are both D. I mentioned in the log base 10 question that there are two very important logs that are so special we give them their own names. Log base 10 is one of them, and then log base E is the other one. And so we call log base E the natural log, or ln. So when you see ln, you might think, oh, we're not dealing with logs anymore. No, it is a log. In fact, it's log base E if you really want to write it out. But when you get kind of beyond this course, especially in calculus, people love talking about natural log ln. So just kind of get used to that notation as opposed to log base E. The log base 10 is slightly less important. You could be justified in asking, oh, what is the base of that? Where if there is no base, where ln is just so standard, it's important to kind of know the relationship in between the two. And in fact, at this point on, I would recommend not writing log base E. Just know that that is the same thing as ln. Also, I don't know if I've used those double arrows before. That's a cute math symbol that means they're the same thing. They're equivalent. So if you ever see that in a math book or see it when I'm going through something, that means I'm going to be able to use them interchangeably. And then I mentioned it's called the natural logarithm. Now, let's get into actually solving a logarithm. We're outside of the translations. Translations are cool and helpful, but they're kind of just a part of the process. So in this case, I'm actually going to find what log base 2 of 8 is. I want to solve for y. So as I mentioned at the beginning of the section, logarithms are quite terrifying to people. So instead of saying, okay, let's be scared and deal with these logarithms, we want to maybe change them into something that is hopefully slightly less terrifying. So that's the entire reason we went through that last slide, is to get these translations going so that maybe there's an advantage to see it in another form. So in this case, if you don't know a lot about logarithms, let's translate that right into an exponential. So it's a log base 2 of 8. I would move that base to the left side of my equation. It will become 2 to the y is equal to 8, just with one translation. Yeah. And so this is where I talked about it on the very title slide, is if you feel not great about your exponentials, this is probably going to be your biggest roadblock, is when you see this, I would kind of expect you to kind of connect the dots here and say, okay, what could I take 2 to, or what power of 2 gets me 8? Okay, well, even if you aren't great, we can think about it. 2 to the first is 1, or 2 to the first is 2, 2 squared is 4, 2 to the third is 8, and so y is equal to 3. And so log base 2 of 8 is equal to 3. And that's kind of the connection that I want to hammer home, is that it seems like logs are weird beasts that follow their own rules. Well, if we can translate it into an exponential, they're not as terrifying. So let's see it again. Y is equal to log base 27 of 3. I'm going to translate it again, so I'm going to move the 27 over. And so I get 27 to the power of y is equal to 3. Now this one's a little bit trickier than the first one. So I need to figure out 27 to what power gets me 3. And it feels kind of weird because when we think of powers, we think of things tending to increase, and increase pretty quickly as well. In the first one it was 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16. 27 to the first is 27. And 27 to the second, I don't have that memorized, but I think it's 200 something, 270, unimportant. So somehow we have to figure out how to make 27 smaller using a power. We saw this, it's been a while. We've seen this though. This is like a square root or a cube root situation. So again, this is if you are really comfortable with your exponentials, maybe you recognize, okay, I don't know 27 to what power gets me 3. But if I cube root 27, I will get 3. So with that in mind, if you know the cube root of 27 is 3, well, we just have to remember how to represent the cube root. As a rational power, 1/3 is equal to a cube root. Just like 1/2 was equal to a square root, just like 1/4 was equal to a fourth root. So all that's to say, 27 to the 1/3 power will get me 3, so my y is equal to 1/3. Cool. Now I still want to evaluate this question, but you might notice between A and B, we kind of started with a y, and C, we don't have anything. And so it feels like maybe we can't really translate this question. Like we had this neat trick that was working, and maybe logarithms were hopefully starting to click, and now I can't translate this, so maybe the trick was pointless, and why did we learn it? Well, we can still use it. We just have to kind of write in the y ourselves. So I'm trying to find log base 4 of 1/4. Just going to say that's equal to y. Why not? You could say 6, or not 6. You could say x or z or w, whatever variable you want to. So if you're just given a logarithm and you're asked to evaluate it, just fill in a variable. Say, okay, I want to find out what this is, and in order to translate it, I kind of need to have it equal to something. I'm going to put this placeholder in to figure out what it is. And then from there, you follow the exact same process in A and B. You want to translate it. So I have a log base 4 that's going to move to the other side of the equation. It will be the base of an exponential. And so I'll have 4 to the y is equal to 1/4. And again, this might seem kind of weird to take something to a power and get it smaller, but it also falls into the category of once you've seen it once or twice, you'll see it time and again. Okay, 4 and 1/4 are related because I could flip 4 and put it over 1 and I would get 1/4. So anytime we are trying to move a base to the bottom of the fraction or move the bottom of a fraction to the top, or really just honestly flip a fraction, we have to have a negative power. So in fact, in this case, 4 to the -1 will get me 1/4. And so y is equal to -1. And yeah, technically I didn't have y at the beginning, so I should just say log base 4 of 1/4 is equal to -1. That's just like getting super nitpicky with notation. I'm sure, I mean, I won't care about it, and I'm sure in the future no one will be like, wait, I didn't ask for y. I can't predict the future. Couple of log properties to keep in mind when we're going through these next couple of sections. Log base 2 of 2 is equal to 1, and log base 2 of, well, let's mention that one. So anytime that I have the base and the input of a logarithm matching, it's always going to be 1, which makes sense a little bit. If I translate log base 2 of 2, then I would get 2 to the y is equal to 2. So what number is equal to itself? It's 1. So anytime you see those two things matching up and you don't see a power, you just say it's 1. Now, if they match up and you do have a power, well, those things cancel out and you're just left with whatever the power is. So log base 2 of 2 to the third is equal to 3. Oh, that's kind of how I wanted it to break down. Okay, well, log base 5 of 5 is equal to 1. Log base b of b is equal to 1. So anytime those bases are matching, they're equal to 1. And now we have matching as well. Log base 3 of 3 with the power of 7. The bases cancel. I'm left with 7. And this works for any base. So if the bases are matching, I cancel the bases and I'm left with just the power. Log of any base with the input of 1 is going to be 0. So log base 20 of 1 is 0. Log base anything of 1 is equal to 0. So watch for that. These are properties that you could probably figure out if you have a little bit of bonus time on a test, or you kind of blank on them. But if you kind of can commit these 2 or 3 or 4 to memory, then when you're solving big problems, it'll be easier to see of like, oh, cool, I don't actually have to solve this. I know just log base 20 of 1 is equal to 0, and I'm done. And then this last thing, I think we will cover a little bit more, if I remember correctly, in the next section or maybe the section after that, but it's called the change of base formula. And so how the change of base formula works is, I kind of mentioned when we just talked about log in the very first time we saw log base 10, how some calculators are fancy and can type in logarithms exactly how we want them to. Some of them, like I think I have a TI-81, I want to say, it only has log or ln. And so in order to use that to evaluate a log of something that might not be super nice, you use this change of base formula to say, okay, log base b of a is the same thing as log base, whatever your input is, log of a, over log of b. And in fact, that actually works for any log. So you could do that with a natural log. You could do log base 3 if you want to for some reason. I can't really think of a whole lot of scenarios where that's helpful, but you can. And so that's kind of the things on this page. This last one is, I definitely would not say memorize, because we will see it later and we will talk about why it's important. Where the things above it, like it's 3 things, and really 2 of them are so heavily related that it's only 2 things. And so the 2 things are, if your bases match up, it's equal to 1. If it has a power, it's equal to the power. And then any log of anything to the 1, or that has an input of 1, is equal to 0. To kind of really hammer home the connection between the two. When we talked about an exponential, the exponential domain of an exponential is always -infinity to infinity. The range of an exponential, unless it's been transformed, is 0 to infinity. Well, a logarithm is, you just flip those. So the domain in this case will be 0 to infinity, and the range will now become -infinity to infinity. So if we're trying to find the domain of a logarithm, we kind of use a process. So when we talked about domain a while back, I mentioned at the time that there's 3 types of things we'll see in this course. There is a fraction, and there's a process to find the domain of a fraction. There is square roots or roots, and there's a process to find the domain when given a square root. And then there was, quote unquote, pretty much everything else, where this is the time that this breaks that pretty much everything else. That's not to say forget that whole process, because it still holds entirely true, but we just have to add kind of one little additional thing to the everything else section. And so that's logarithms. Logarithms do have their own domain. When we get into solving logarithms, we need to be checking our answers again, because we can have extraneous solutions. But as far as the process goes, it's the exact same process as a square root. It's just, instead of greater than or equal to 0, it's just greater than 0. So that's why I'm saying the method still works, the 3-type breakdown still works. It's just, when you see a logarithm, think, okay, it's square root, and now it's just greater than 0 versus greater than or equal to 0. So to see exactly what that means, we have this logarithm. We take whatever is inside. I don't care what the base is. I take whatever is inside x minus 4. I'm going to set it greater than 0. And then you just go ahead and solve. Add 4 to both sides. So my domain is 4 to infinity. Now, as far as kind of just a very brief introduction of logarithms, the graph on the left is not a logarithm at all. It's an exponential. We've seen that before. What a logarithm is, and this is how you graph any inverse. We've talked about this before, I believe. Yeah. Is we draw a y is equal to x line, kind of a dotted line that's not even really there, and we flip it over that line. So the graph on the right, again, the top thing is still my exponential, but the bottom thing in blue or maybe purple, depending on how you look at it, that is my logarithm, and that's because it's an inverse. And if you look at that graph, oh, okay, yeah, the domain is 0 to infinity, the range is negative infinity to infinity, and we're going to talk about some other properties. But that's where this comes from. If you had never seen a logarithm before, you wouldn't really even need to know specifically what a graph looks like, because there is this relationship. And that's where the shape is kind of coming from. Okay, yeah. And so when we talked about exponentials, the parent function standardly, but not always, or typically, was y is equal to 2 to the x. And in this case, unless otherwise specified, generally we talk about the parent function of a logarithm to be log base 2 of x. And so that's what the blue graph is. Now to talk about kind of all the properties, just like we talked about them when we were dealing with an exponential. If I have a function y equals log base b of x, my vertical asymptote is going to be x is equal to 0, which makes sense because my domain is 0 to infinity. My range will be negative infinity to infinity. My x-intercept is going to be 1, 0, and this would be true of regardless of what your base is. So b could be 3000. Your x-intercept is still going to be 1, 0, and that feeds into, or that comes from kind of the fact that we ended the last lecture with log base, anything with 1 on the inside will always get you a result 0. And another property, again discussed in the last lecture, is if those bases match up, your output will be 1. So the other key point we deal with logarithms is always whatever your base is, 1. And yes, I think up to this point, every parent function we've seen has 2 or 3 key points. This one's only going to have 2 because you start to get really weird functions from there. But you could figure out another one by just plugging in a point. Really weird values, not functions. And then your y-intercept is going to be none unless you transform your graph a little bit, because, I mean, that makes sense. Your x, or your vertical asymptotes, x is equal to 0, so there should be nothing crossing your y-axis. This is the graph. The top one is if your b is greater than 1. And the bottom one is if your b is between 0 and 1, just like we had with exponentials. One is going to kind of have that arcing curve to the right going up, and the other one's going to have that arcing curve going down to the right. So if we're going to graph, seems kind of terrifying. We just learned about logarithms, and this seems like a bunch of weird numbers flying around in this question. I should have said y is equal to 3 minus ln of x minus 4. I apologize for that. Maybe I fix it in the next line. Nope, I do not. But that's fine. We have the properties. We're going to write down our key points. We're going to write down our transformations because we've seen all of these transformations before. We're going to apply them, we're going to plot points, and we're going to graph. So yeah, seems like a lot, but it's something we've done twice, if not 3 times before. So the key points are going to be, well, 1, 0 is always going to be your key point regardless of what the base is. And then your other one is whatever your base is, and then comma 1. So we know ln is log base e, so my other key point is e comma 1. Now you might be thinking, okay, Zach keeps talking about this e, it's not really a value. No, it still is, and when we get to actually plotting our point, we'll talk about strictly what the value is. But for now, just imagine it's a placeholder and still just go through your process as though it was just any other transformation question. So the next step in the process of a transformation question is to describe the transformations. So looking at my 3 minus ln of x minus 4, my first transformation is I'm shifted to the right 4. That's what's inside my log. And then my second transformation is the negative outside means I'm flipping over the x-axis. So that means I'll be multiplying my y by -1. And then my last transformation is up 3. So now we apply them. First one is moving to the right 4, so I'm going to add 4 to both of my x values. My first point will become 5, 0, and my second point, like again, you could probably put this as a decimal if you wanted to, but for now let's just leave it as e plus 4, comma 1. And then my next transformation is reflect over the x-axis, so I'm going to multiply my y values by -1. So my first point is actually not going to change. It makes sense. 0 times -1, 0. And then my second point is going to become e plus 4, comma -1. Last transformation is up 3. So I'm going to add 3 to both of my y values. My first point is 5, comma 3. My second point is e plus 4, comma 2. My vertical asymptote is not at originally is at x is equal to 0. Okay, yeah. So my vertical asymptote for my parent function is at x is equal to 0, but now it is being shifted to the right 4. And so if you don't really even see that with the shift, you could still kind of go back to when we found the domain and realize that x has to be greater than 4. So now my vertical asymptote has shifted to the right 4, so instead of it being x is equal to 1, it becomes x is equal to 4. Instead of it being x is equal to 0, it has become x is equal to 4. And now we're going to put all of our pieces together in a graph. So my first thing that's easy to plot is x is equal to 4. That's just a vertical line. I drew it as a dashed line, which is kind of typical when we're dealing with asymptotes. Then 5, 3 is certainly doable to see. I plot it on 5, go up to 3. Something that is worth mentioning is the grid on this is a little bit weird. So they aren't spaced by 1s, they're spaced by 1/2. So my red line's on 4. My next line to the right is 6, or my next bolded line is 6. And so in between those is 5. So that's where that purple dot is showing up. And then I have to plot e plus 4 plus 2, or e plus 4 comma 2. So my horizontal line right there is y is equal to 2. And then now we're finally going to have to evaluate what e is. E, like I mentioned, is 2.7 something. So it's 2.7 something plus 4. I would definitely throw it in a calculator if I was you, which becomes 6.2 something. So now we're going to put all of our pieces together in graph. So I'm going to plot my vertical asymptotes at x is equal to 4. It's that dashed line. I'm going to plot 5, comma 3. It's worth mentioning my grid's a little bit strange on the graph that we're seeing. And so it's actually going up. Each box represents 1/2 versus 1. So right between 4 and 6 is 5. And then 3 is going to be, it's actually going to be 6 tick marks up from the bottom. And then my black dot is e plus 4, comma 2. And this is one of them. If you were sketching by hand, you would have to use a calculator or something. It ends up being, if you add e to 4, you end up getting 6.7 something. And then at 2, which is that bolded line horizontally. And so then we know, okay, we're dealing with a log function, and log functions are either going to kind of start from the bottom and swoop to the top, or stop from the top and swoop right to the bottom. And since this is being reflected, it is going to start from the top and swoop bottom to the right, which makes sense the way the points are lined up as well. So I would just draw a line that goes through those 2 points, make sure that I don't cross my vertical asymptote, and that is my graph. Now if we want to go the other direction, and this is kind of how I ended the exponential graphing as well, we can either describe an equation to you, or we can give you a graph and make you translate it from the graph. So in this case, we have the graph, and I want to write a logarithm equation that will model this graph. So we kind of have to identify our pieces of information. Again, the grid's a little bit strange with this, but the vertical asymptote is at -3. And I have some points. My point is at -2, -1, and at 1, 2. So with that information, I know at least that my graph has been shifted to the left 3. So I can say, okay, I don't know overall what my logarithm function is going to look like. I'm going to choose my base as just log base 10, because that's the easiest to deal with. And then I'm going to say, okay, I know that shifted left 3, so I have log x plus 3. I don't know what I'm multiplying that by. I don't know if I'm being shifted up or down, anything like that. So I'm going to kind of just put placeholders in there until I figure out what's happening. I think what probably would happen in WebWorks is they're going to tell you what base to use, but if they don't tell you which base to use, I would recommend using log base 10. So now we're going to plug in some values to figure out what these missing variables are. So I'm going to plug in my first key point, -2, -1, -2 for x, -1 for y, and then I'm going to simplify from there. So then my -2 plus 3 gets me 1. We know that log with an input of 1 is always just 0, so that actually goes away, which is nice, because now we have k. K is equal to -1. So I solved for one of those variables in that kind of the middle equation the equation in the middle of the slide, and now we want to find my a. So I plug in my k, and I plug in my point now, the other key point, 1, 2. So my x becomes 1, my y becomes 2, and then again, now I'm going to be solving for a as opposed to k. I go about solving for a. So I add 1 to both sides. I divide both sides by I divide by both sides by log 4, and so that's it. I could round that if I wanted to. Like I could get a decimal of 3 over log 4, but why do extra work if you don't have to? So this is a perfectly fine way to write out this equation. Y is equal to your a is now 3 over log 4 times log of x plus 3 minus 1. Now getting back into logarithms. If I have a logarithm and I kind of have some other stuff lingering around, I want to get that logarithm by itself. So I'm subtracting 6 from both sides. Get ln of x is equal to 4, and then this is just a simple translation problem from there. Ln is the natural log, so that's a log base e. If I translate that, I would move the base over. I would get x is equal to e to the 4th. Very similar concept with this question. I have 2 times ln of x plus 1 is equal to 10. I divide both sides by 2, and then now I have my logarithm by itself. It might not feel that way because I have an x plus 1 in this case, but that x plus 1 is in parentheses. Not really even in parentheses. It's my input of my logarithm, so I can't move that -1 over. In this case, I'm going to translate at this point, so it would become x plus 1 is equal to e to the 5th, and then I would just subtract 1 from both sides.